My name is Tobias. I work at a company called Neo Technology. Every once in a while they let me out from the office and let me go to conferences like this, or let me work on cool things like what I'm going to talk about today. Maybe you don't think it's cool, but I hope you think it's cool because you're here. But I think this is super cool. I live on the internet here, various places. These slides will be available somewhere. If not, if you can't find it through Oracle, find me as Thobe on SlideShare, and it's going to be there. I'll upload it there after the conference. And the reason they let me out to do this is because I say things about them, like I put their logo in here and say how much I love working at Neo Technology. What we do is we build a database management system, which is kind of it contains quite a few bits of really cool technology in there, which is why I love working there. And if you want to know more about that stuff, I've got a talk on non-relational databases on Wednesday. And Neo4j, our product, is going to be featured in there. Enough about that. Let's get down to it. So these are the things that I'm going to be covering today. A few of these you might know. Probably you know the Java debugger interface. I'm assuming if you've written code, you've used the debugger. I'm going to be doing things you never thought was possible with it. And then I'm going to be looking at some things you might never have seen. Or maybe you have. But I'm going to be putting them all together and make crazy things with them. So let's start with java.lang.instrument. It's a package in the JDK. It's a standard package included in all JDKs. It contains a few interesting things. Like one of the things, when I got to Java from other programming language, I was missing the size of operation. Not because I needed it for the things that you need it for in C, such as allocating data of appropriate amount, but because I wanted to introspect these kind of things. How big are my objects? Because that relates to the heap usage. I know how big my heap is, but how large are my objects? How many objects can I fit in the heap? So the size of operation is I thought I was missing. I found it in java.lang.instrument. Granted, it wasn't added until a few years after I declared that I missed it, but still, it's there now. It also contains a few other cool things that allows you to introspect what the VM is currently doing, like getting all loaded classes, getting all initiated classes from a particular class loader. There's a slight difference between loaded and initiated. An initiated class, the difference is that the initiated class has had the static initializer run from it. So all of these static fields and such things are populated. Then it also contains really cool things on redefining classes. So you can take any old class and with this instrumentation API, say that this class isn't actually what I wanted. I'm going to redefine it at runtime. So redefine methods, add and remove fields, whatever. Which is kind of cool. I haven't used this much, but I know that there are, for example, testing frameworks that use this. I just wanted to let you know that it's there. I don't do class transformation much. I prefer to do class transformation on the actual class file before they're loaded, if I need to do that. But if you want to do it in runtime, which some mocking frameworks and such things do, this is how they do it, by using Java.lang.instrument. So how do you get to these things? How do you get to the Java.lang.instrument? That's where we get to the hidden part. So you know how there's a magic method in Java programs with the signature public static void, the name main, and the that takes a single argument of type string array. There are a few more of those magic methods. One called pre-main. which is executed in something called a Java agent. So Java agent is a jar file containing class files. We all know jar files containing class files. Those are simple. We also know that there's a metainf.mf file. Metainf / manifest.mf file. Which contains some information about the classes in the jar. For example, the main class, which contains the main method. So if you just run the jar, it will run that main method in that main class. There's also a few other directors that can use for agents. For example, the pre-main class, which is essentially same thing as the main class for things that have a main method, but is for the pre-main method. And this pre-main method is public static void again, called pre-main. It takes a single string argument and optionally an instrumentation object, which is the entry point to the java.lang.instrument APIs. When I say optional, you can declare this method both with and without that instrumentation parameter. So just declaring the single string is also valid, but you won't get to the good stuff if you do that. You can also define extra things to add to the class path for the agent, and define the capabilities that you want the instrumentation API to provide to you. If you wanted to redefine, be able to redefine classes, retransform classes, and set native method prefix. Not very interesting. You can read up on that later. I'm going to post references at the end. The interesting part is you get to the instrumentation audio through this. You load it by specifying on the class path, saying Java regular parameters on the command line. And then you specify that you want to load this Java agent, -Java agent, : and the jar file. And then you can say, optionally you can say equals and then some options. And those options are going to be passed as that string agent args argument. So that gives you something, an entry point to getting to instrumentation. There are cooler ways of doing this. So that means that you have to start your JVM knowing that at some point I might need this instrumentation. I want to start it with instrumentation enabled, which is good if what you want to do is redefine and transform classes, such as those mocking frameworks I talked about do. But you can do even cooler things. There's something called Java agent. So as you saw in the command line thing there, this is called a Java agent, but there's another kind of agent, which has an agent main method. And the difference between pre-main and agent main is that pre-main gets executed before the main method gets executed. If you specify the Java agent on the command line. The agent main gets invoked when an agent visits the JVM. So you don't specify it on the command line. Instead, you have the agent discover the VM and enter it after the fact. And it can still do the kind of things that you can do with instrumentation, the pre-main stuff, and get size of objects. But what this allows you to do is and that I use it for at work, is for adding code to my running application after the fact. For example, in our database, we have a plugin architecture where I can, where I say that, so this database is started, it's running. Actually, I want to add some capabilities to it. So I start a small Java program that all it does is bootstrap into that JVM with inject an agent, and that agent discovers the database running inside the JVM and adds capabilities to it. So I load and add code on the fly by using Java agents. Oh, I had a slide on that. Sorry. And this, for example, is also how how some of the functionalities in JDK, in the JDK itself works. For example, if you've ever used the JConsole application, you know that you can use it for attaching, introspecting JMX variables through a long and complicated connection string. You can also just specify a process ID. You just connect to a process running locally on your computer. That thing uses Java agents. So what it actually does, and I think I have, yes, on the next slide. There's a hidden API. So this is where we get into some proprietary APIs. Some doesn't exist anymore, so I guess it's Oracle proprietary APIs. I think at least a few of the other JDKs specify this API as well. If not, they should have equivalent APIs. This is the API for attaching to a JVM and injecting an agent. In this example here, this example code, it's actually from the actual JConsole source code. I've simplified it just a little bit, but that is essentially what it does for starting the JMX agent that allows you to connect to it through JConsole. So when JConsole is started with a process ID, or when you specify a process ID in the interface, what happens is that it uses this com.sun.tools.attach virtual machine API to attach to that process ID. I've used 1337 as a placeholder for process ID here. And then it reads the properties of that virtual machine. Also kind of a cool feature. I'm in one Java process reading the system properties of another Java process. Quite funky. It gets the Java home of that. So it gets the location of the system libraries for that VM. So it can load the management agent jar from that's supposed to go with that VM. So it gets that agent, then says load the agent, and gives it a parameter. So this is again the same kind of thing as with the pre-main. We specify Java agent on the command line. We give it the location of the agent jar file, and and the options for it. So this is the location of the agent jar file, and this is the options. So we do that. We are attached to the VM. We load the agent in the appropriate location, and then we're done. We don't do anything more in this process, because the rest of the stuff is going to happen in the process into which I injected the agent. So we just attach. And then what's going to happen there in the case of JConsole, and that's where the bulk of the code is what happens inside the agent, is that it's going to open up and listen to this port that has been specified. And I think 5000 is actually the default that it uses for this, although I think it might allocate ports at random. But the thing is that it's the process that starts the agent, or that injects the agent, that decides the port. So after we detach now, we know that there's now going to be a port opened on that I can connect to and get the JMX parameters. So it didn't have JMX the JMX server started before. I injected an agent that started the JMX server, and now I can get to the JMX beans. So that's how JConsole works. If you didn't know that previously, you know it now. Also JPS, if you ever use that command, it lists Java processes. That also uses this same API. So it's possible from this virtual machine API to not only attach to a virtual machine given its process ID, you can also list all running Java processes and attach to them. So I do that with the plugin capability that I mentioned. If I have multiple databases running on the same server, I connect to all of them and say I want to add this functionality to all. It's kind of handy. And usually the functionality I add is also I start a port where I can get a remote shell access to it, because the database doesn't start with that normally. Here's the trick I use for that. For listening to a port, I use RMI, and RMI is crap. Don't use RMI. But for stable environments, like communicating between processes on the same machine, where you don't really care about the performance of the protocol and such things, it's really simple to do stuff with RMI. You just define your interfaces, declare a class that extends unicast remote object and implements your interface, and then you're ready to go. The hassle with RMI is the thing with registries. So if you want to do RMI, first of all, use it only for things on the same machine, because it's not really something you should use for distributed systems. And don't use registries. They're a mess. So what an RMI registry does is that it's essentially a list of, or it's essentially a hash map running in some Java process that I can connect to, that has a hash map from an identifier to a serialized RMI stub. So I go into that process, go into the hash map, get the stub that I'm interested in, and I deserialize it in my process, and I connect to it. Super simple. So the RMI registry doesn't actually do anything. It just holds these serialized objects. So all I really want to get to is one of these serialized objects. So how about I just pass that along straight away? Then I don't need to mess around with registries that are hard to maintain, and I need to have them running on a known location, known host, known port. I have to make sure that something is up and running there. If it isn't, I have to start it. It's a mess with registries. Don't use registries. So instead, you can just serialize the object and pass it on your own. So as you saw with the agent injection, you can pass an arbitrary string as parameter to the agent. So why not just serialize an RMI stub in there, pass it on, serialize it to a string, which I usually do by just serializing regular serialization to a byte array, and then base64 encode that to a string. Simple enough. That means that you now have a way to talk back to, from the process where the agent was injected, you now have a channel for talking back to the process that started the agent. Pretty nifty. And then of course you can for getting a way to for talking from the process that started the agent to the process that was running that now hosts the agent, you can of course have it just send a callback to the initiator, and now you have a two-way communication link. Oh, code demo. Not this code, other code. I have to find it. Callback agent. So this is code that does that, and a few more things. The main thing here is the inject into. That's what I wanted to click on. Which what it does is that it does the same thing as the JConsole example I showed. It attaches to a virtual machine, and then deploys an agent to it. And what I do here is I load the agent by getting the jar file of it and then serializing it. So I get the jar file that contains the agent classes, and I get the serialized version of the agent, and I send it to it. That's my API. Serializing basics for encoding. And serializing is, of course, a simple byte array object output stream wrapped in a object output stream. So I write an object and get a byte array. Simple. But what is it I actually serialize? So this agent is something that contains other serialized objects, actually. A stub and an invoker. So this is very generified. This is a library that you can pick up and use on your own. It's available on the internet, on my GitHub account. You can play with this if you want to. So what you do here is you have you create a callback agent. You give it a callback, which is something that extends the RMI remote interface, and then a callback invoker, which is just an interface that invokes the callback, and it gets a few objects from the target VM that you can use, like the instrumentation and also some misc unsafe. Because I like to lib unsafe. So what happens is that it calls the agent, and then in the agent main here, we deserialize the agent, and then we load with the instrumentation. So, yep, deserialize the agent. So we pack two things into the same object and serialize them together. Deserialize it, get the callback and the invoker, and then just invoke the callback in the new target VM. Simple. And that gives you, that is a generic way, that's generic code I wrote for deploying your own RMI interface into a separate VM. So you can have your code in the invoker. You can do whatever you want to get whatever state from the target VM you want and pass it into to the callback of your choice. I mentioned that I was going to look at the debug interface. Here's something that I built using the debug interface. So I had a problem once. Can I do this in full screen? We had some issues. So Neo4j, the database that I'm working on, has been around, was built in 2001 first. And we've been working on it since. And at some point we realized that we didn't have enough test coverage on a few concurrency cases, and the code wasn't written for TDD. This was before, way before TDD. It was built in-house in 2001. So external users do things a bit differently, which leads to interesting new use cases and interesting new issues. And many of those are around concurrency. So 2001 was before TDD was very popular, so it didn't have full test coverage. And it was one big monolithic code base. I didn't have components that I could break out and test separately. Instead, most tests were done on the full database. It was mainly just the tests that were in the code base were mainly essentially integration tests. And I wanted to test very specific concurrency cases, and I couldn't break things apart quick enough to actually get turnaround on the issue to help our customers in time. So what I ended up doing was I wrote a test, a full integration test that reproduced the problem. And I guess that this is what most people do when debugging concurrent issues. And then and I of course assert that there are tests covering the current behavior. And then I changed the code. What the hell? Right, that's how you do testing. Many of these issues were around concurrency. And And the thing about concurrency issues is that they only manifest if all conditions are just right. Or wrong, as it may be. And so some way we have to control the internal behavior of the database in order to get to that right state for the bug to manifest. And that's hard when you got one big monolithic code base. So what I did was I used my debugger, set up thousands of, not thousands, but lots and lots of breakpoints, and stepped through in a very particular order, making sure this thread got that far, then that thread gets that far, and then this other thread gets that far, and now it's in a weird enough state that if I tell this thread to progress, it's now going to enter a bad state, which means that if the other threads continue, things are going to break. That is hard work. Just remembering all of those steps in the right order, it's insane. So I was sitting with 20-something breakpoints, some just for making sure that I was at the right point and didn't overstep, and then pen and paper to make sure that, okay, now I'm here in this state. What should I do now? Enable this breakpoint, disable that breakpoint, run. It was insane. So what I did, right, so we reproduced the condition in the debugger. But what if that debugger was my test case? What if I could automate the work that I did with my debugger, all of that tedious stepping through in breakpoints? And so I did. I created a JUnit test runner based on the Java debug interface. It's a regular JUnit test runner, and this is roughly what it looks like in the Neo4j codebase. I started breaking this out into its own separate library, so the second generation of this this code. It looks a lot nicer now, but still, this is what it looks like in Neo4j. It's normal JUnit test cases, but the twist is that they execute in a subprocess. So the actual test cases, these methods, execute in a subprocess that I've attached a debugger to, or that the host process is attached to an automated debugger to. And then the host process run handlers for breakpoints in that code. So that's essentially what a test case could look like. And that solved the immediate problem for us in that we had to quickly, within days, find and reproduce, fix an issue, make sure that we had fixed the concurrency issue, ship it to customers within just a few days, so no time to refactor the entire code base to allow for proper testing. And it worked. So that was one thing that I thought could be useful to share with people. So I wrote a library for that. I publishing that as an open source library for everyone to use. And the API looks a little more like this now, which I believe is a bit simpler. Unfortunately, not everything is ported yet, so it doesn't. There are a few edge cases that doesn't quite work. With these breakpoints yet. So what you say is, I have a regular JUnit test case. I say that I want this to run in a subprocess with the subprocess TestRunner. Then you say, you just have your test code as usual, and you say, I want to debug this. Where's the pointer? I want to debug this using the breakpoints defined in some class. And then you define breakpoints by specifying that this method is a handler for, and then specification of the breakpoint. And so far I've found that it's good enough to be able to breakpoint on method entry and method exit. I haven't really had the need to break on a specific line in the code I've used, because a specific line usually is the entry to some other method, so I can just breakpoint on the entry of that method instead. So that code's available on GitHub as well. And I've used this library that I've published there for testing all of the other code that I've written here. Turns out that testing things in a subprocess, like particularly controlled subprocess, is useful even if you don't have the need to debug it. Testing things in a subprocess and specifying parameters for the process, like I want to run in an environment that has a very particular memory setting. It's also useful. So subprocess TestRunner is quite a useful thing, I think. Next cool thing. This is where it starts to get really scary. And I should have mentioned that so far it's been 100% pure Java. From now on it's going to be 100% unpure Java. So there are a few things that you can do in the JDK, still standard JDK APIs, they're just not in Java. So a few cool things that you can do if you venture outside of the comfort zone of Java managed code. The JVM-TI interface is one of those APIs that is it's actually a C API for the JVM. It's standardized, supported by all JDK vendors. And it has some pretty cool abilities that you can do. You can walk the heap by following references. You can start at a root object and follow references, kind of like the same thing as the garbage collector does. And in fact, in OpenJDK and I guess Hotspot as well, because they're essentially the same code base, this actually piggybacks on the same thing as the same code path as the garbage collector uses. There's also the ability for tagging objects, which is also, incidentally, what the garbage collector does. Mark and sweep garbage collectors do exactly that. They tag objects and then discard the objects that aren't tagged. So you have the ability to follow references, tag objects, tag classes, but also the ability to collect all tagged classes. So I can say, give me all the objects that I've tagged with a particular tag in a list. Or iterate through all reachable objects in the entire heap, or iterate through all objects in the entire heap regardless of whether they're reachable or not. So you can actually get to dead objects through this API. And you can iterate through instances of a particular class, like all instances of runnable, for example, or all instances of string in your entire heap. And of course, the same things as you can do with the java.lang.instrument, getting object size and getting also getting object monitored usage. Do I have some cool demo for this? I think I do. So I have Heap access test. A test case for this I can show you. So what this does is, boringly, it gets all instances of the test class itself, and then asserts that it gets this. It's the same way of testing that this works, and not very interesting. What's more interesting is, for example, getting all runnables. So you can get all instances of java.lang runnable in this JVM, which is kind of cool. And I can do this with any class. So I've created this API that I call tooling interface, which is essentially a Java representation of the JVM TI. So TI is for tooling interface, which is why I call this class tooling interface. So this is a pretty simple API on the Java level. All it does is it just hands off to some C code. Just hands off to some C code, some native code implemented in JNI that calls the JVM TI. JVM TI is an extension of the JNI. You never thought you'd hear someone talk about JNI in 2012, did you? So this allows me to walk the heap and get all instances of this object. And actually the C code for this isn't that horrible either. All it does is that it uses this JVMTI interface for iterate over instances of class. So iterate over the heap, give me call this callback method here called tag object for all instances of class that I specified. And what the tag object callback does is just that it sets the tag on the instance. And then after that, what I do is I get all objects with the tag that I specified, and then I create a Java array after that. So up to this point, let's see, this section is JVMTI, then the rest is just regular JNI for creating an array and populating it with the objects I found. So that's pretty cool. What's even more interesting that you can do with the JVMTI interface, and what got me into looking at JVMTI in the first place, is the ability to introspect the call frames of a running method. So I was 5 years ago, it was that I first looked at this. I was working on a project called Jython, which is an implementation of the Python programming language for the JVM. And one of the biggest overheads there is managing call frames. Because Python has this nasty ability that lets you inspect any call frame and getting the local variables by telling you what the name of them is as a string. Do that for any old method. And managing extra call frames on the heap is quite a big overhead in Jython. So I wanted to look at, is there any ability that I can use the actual JVM internals for getting to this? And so I did. I talked to one of the JVM developers who said, well, you can just drop down to native code, write an extension for the JVM, build your own custom JVM, and do it through there. I was like, oh, that's going to be a mess to deploy. I don't want to maintain my own JVM version. So I found JVMTI, and found that it had some abilities to do frame introspection, which meant that I could do this as a regular dynamically loaded JNI library. So I did. So I created a Java API for accessing the live call frames of the current thread. Could be extended to other threads as well, but so far only to the current thread. And for introspecting the live call frames. And this builds on the frame introspection abilities on the JVMTI, which allows you to get the method that is executing in that call frame, get the bytecode of that method, get the offset in that bytecode where the JVM is currently executing. You can pop the frame and rerun the method. Popping the frame means go one step up in the call stack to just before you enter this call frame. You can also, and this is the interesting part, get local variables from the call stack, from a frame, and set the local variables. You can also register an event hook in the JVMTI interface for getting a callback when the frame is popped through normal means. So when it exits through a return or a throw. So forcing a pop frame does not trigger that event. So I don't use forcing pop. And getting that notification is actually quite crucial for knowing whether a reified call frame object in my Java library is live or not. So whether it could go down to the underlying call frame and get objects from there, or whether that call frame is no longer available. Again, test case for this. So here's the first test case I wrote for that. Should access live call frame of current method. So it defines a bunch of local variables of various types, because I want to make sure that I can get to all of those different types. And I get the call frame at depth 0, so I get the current call frame. And then I assert that if I get the local variable a from the frame, it is equal to the local variable a. But also, if I change a, I should still get the new changed value from my reified call frame objects. And does this test case work, or do I have to run it? No, it doesn't work when running through the IDE because it has to load the agent in various weird ways. I can't show this running, I think. Okay. No. Runs from the command line. The code for this is slightly more involved than the code for walking the heap. Actually, most of this C file weighs in at just under 1,000 lines of code is for managing call frames. But we can look at the Java side of things is actually quite simple. Yeah, so for managing whether a frame is live or not, all I do is I have this callback in the native code in the JVM that when the frame gets popped, when the frame is exited, I get this callback, and then I call into Java again and say, hey, if you have a frame object, a reified frame object for this, please kill it. It's not live anymore. So it's just a simple manager for this. It can push frames and pop frames. No, I'm really, since I don't really care about performance for this, I've just implemented this as a simple hash map. That's also available in my GitHub account. This is where it gets really cool. Putting all of these things together and running a JavaScript engine attached to another process with the ability to do all these kinds of introspection. Here I have a Java process running. You can see process ID here. And I can attach a remote shell to that. I'm going to just rebuild, because when developing, I like to have scripts that just do the full rebuild, so I always have the latest build. Succeeded. And now I have a remote shell connection to this. So here I can do java.lang. And this is just regular JavaScript. Let's call get property. It's going to bootstrap and create a connection. Timeout. Crap. Oh, look at that. Something happened. let's start this with some property. Oh. That's why. Rebuilt. Okay, so it's running. That's my new process ID. Let me just uncomment this. There. Get property. There. Could get the property from the remote VM. So I have this VM running here, and I've got another JVM running here, which is running a script engine that's connected to this VM. So the script engine is actually running in this process, but I use the script engine from this process, which is kind of useful for debugging live systems. So I have a system running live in production, and I need to look at some of the state of it. And that's also available on GitHub. There. As IntroScript. And this builds on all of these other libraries. Anything else you'd like to look at here? Questions? Yes. Yeah? Okay, so what's the overhead of using decisive method to get the size of an object? Because if you have a large heap and you want to get an accurate view of the heap usage, you could, for example, do that by iterating through all and getting the size of. I would say that the main overhead there would be iterating over the heap. Getting the size of an object it's not that expensive, but it's not something quite often you don't want to do. You don't really want to have an agent running in your live code. You don't want to depend on having that. What I use the size of method for is for verifying that my pre-computed sizes are correct. So I have where I need to know the size of an object for knowing how much of a heap I'm using. I have data structures that keep track of, that add and remove from a counter of what the current size is. Each object knows its own size. And that can just be a static field on that. And then in my test cases, I verify that field is actually the same value as if I would get the size with the size of method. Down there. So if you do kind of stuff like this, are there any special security concerns? This is completely insecure. The only things I've done to secure it a bit is that I do shake on that tooling interface. The get tooling interface method actually shakes the security manager to verify that you have permission. That's all I do, really, just to make sure that you can install a security manager that doesn't allow you to use this interface. But of course, using it is completely at your own risk and completely insecure. However, it is not, I have made, since I just like playing with things, I have made that check impossible to circumvent, which is not the case for sunmisc unsafe. With sunmisc unsafe, it is actually possible to get the unsafe instance by just using regular reflection if your security manager permits reflection. And there are security holes that allows you to use reflection in any manageable case. What I've done is that I've actually stored the reference to the instance of the tooling interface in C code. So it's not accessible through reflection. 10 minutes? Is that okay? Well, we're in Q&A, so it doesn't matter. Excuse me? Does what work with? On another machine? So the hard part with remote processes is how do I inject into the VM? So the agent attach APIs are VM local, are for local machines, because it uses, so what it actually uses for attaching to a VM is a shared memory buffer that all JVMs share. So that's how it finds out how to get into and inject the agent. So that's not possible over a network. But what you could do is, of course, have a small process running on a host where you could go through that process and say, hey, can you inject into the other VMs on my behalf? And then, of course, since it's RMI, it will work over the network. That, of course, again, is completely unsafe. If you open up holes in your security like that, you're gonna have holes in your security. But it's fun. And for debugging purposes, you often are on the same local machine, and that's what I use this stuff for. What did you want to look at on the slide? Yeah. So here's the links to the code samples. They're all under my GitHub account. But here's references to the API documentations of the APIs that I've used. So when building this stuff, I was constantly flipping through the JVM tooling interface documentation, as well as the JNI documentation. Even if you're going to hate me for this, but I actually like JNI. I think I might be the only person in the world who likes JNI. But even if I do like it, I don't use it that often, so I don't remember all of it. So having these resources available when building this stuff was crucial. And also from reading these APIs, I found that it would be possible to get call frames of other threads than the local thread as well. You would just have to suspend those threads while accessing them, which is a bit of a pain, and I haven't done that. Yes? Yeah. It's the same case here. So that shared memory buffer that I mentioned so Unix systems don't permit you to share memory between different users. That's why. So you can't inject an agent into a JVM running as a different user. So that's really good, actually, because that means that even if we do screw up our security in the JVM in these ways, we can still rely on Unix security to save our back. Yes? License. I haven't decided on license, but I was thinking something very permissive, like MIT license maybe. I really disliked the Apache license because for some reason it's become like a seal of bad quality. I really have a beef with Apache. I hate them. If you're with Apache, fight me later. Anything else? Thank you.